should be all set.
They can hear now? I haven't done anything, so if they can hear,
Yes.
then
We can hear now.
excellent. Okay. So I just asked for any questions, and I'll try to save a few minutes at the end of today's lectures to ease whatever anxieties you have about today's exam. But let's just go into a review of what we did last time. So again, as far as announcements, Lab 4 will be posted today. I don't know that it's been posted yet, but since you have an exam today, and because I'll be giving you homework, instead of giving you 1 week to do the lab, I was going to give you till the following Monday, which basically gives you almost, instead of 7 days, 10 days. I'm not going soft, I was just being considerate. So, big step backwards, we talked about forces on plane submerged surfaces. We could take that resultant force and divide it into horizontal and vertical components. And what we did was employ that to use that device, breaking the resultant force into horizontal and vertical components in order to help us calculate the force on a curved submerged surface. And so what we recognized last time is a horizontal force component is basically the force acting on a projection, a horizontal projection into a vertical plane of that surface. So again, when we do those surfaces, that projection is typically a very simple object like a rectangle or a circle or a triangle. And so the horizontal force component is the force on the projection, and the vertical force component is simply the weight of the fluid above the surface or displaced by the surface if the fluid happens to be below the surface. And then the resultant force would be the vector sum of those two. And then I did an example last time. And then where we ended last time was talking about buoyancy and flotation. And basically we said we had this brick that was floating and it's just sitting there. It's not moving, so we can apply equilibrium or static equilibrium mechanics. Sum of forces in any direction would be equal to 0. And what we recognized here is that with this differential sized brick and a depth of submergence h, we would necessarily have already.
I think you should be in presentation mode.
Oh, I thought I was in presentation mode.
No, in bottom right, just click on that.
Yeah, you're right. I'm not in presentation mode. No wonder. I would have spent probably 20 minutes trying to figure that out. So what we have is a pressure distribution at the bottom. And because this is a brick, the bottom is horizontal. And of course, we could make it almost any geometry we want. But the pressure at the bottom would be equal to the specific weight of the fluid, whatever that is, times the depth of submergence h. And therefore, we could not only calculate the pressure at the bottom, but knowing the area of the bottom and the fact that we have a constant pressure distribution on the bottom, we could calculate the force of the fluid on the bottom. And again, this is just due to the pressure of the fluid at that location. And when we look at that force, we can recognize that HA in this case is what we would call the volume displaced. And so this is Archimedes' principle. For a floating object, the weight of that object is equal to the weight of the fluid displaced by the object. And again, something you probably learned in high school. So in the vertical direction, again, since this is floating and it's in equilibrium, we can say the sum of the forces in any direction is 0. In this case, we're going to look at the vertical direction. And again, we typically have z positive upwards. So in this case, the pressure distribution on the bottom that we integrate into a force is called the buoyant force. And in the case of these objects, that buoyant force is again the specific weight of the fluid times the fluid volume displaced by the object. And again, that is no different than the vertical force we were talking about just last lecture for forces on curved surfaces. In this case, you have the surface above the fluid and you're displacing fluid, and the vertical force is no different than what we were talking about last time. It's the weight of the fluid displaced by the surface. So it acts, the buoyant force acts on any submerged or partially submerged object. This buoyant force is basically representing the pressure difference from the top to the bottom. And for a floating object, the pressure distribution on top is atmospheric, or since we're working problems in gauge pressure, that would be zero pressure. And so zero force on the top due to that pressure distribution. And then again, as we go deeper into a fluid, we will always have higher pressure on the bottom of an object than on the top. So as this object becomes fully submerged, there will always be this pressure difference. And so there's always a buoyant force. And that buoyant force is going to be the specific weight of the fluid times, when it's fully submerged, the entire volume of the object. And because the pressure distribution on the bottom is pointing upwards, and it's greater than the pressure distribution on the top pointing downwards, and the net difference is that the pressure on the bottom is larger, the buoyant force is always directed upwards, whether it's a floating object or a completely submerged object. Okay. And the very last line we're going to talk about, obviously heavier objects are lighter in water. So here's a simple example, and I can't remember if, I don't think we got to this last time, but we've got this cube, and this cube is going to be 10 centimeters on a side. And it's got a specific gravity, so S is equal to 0.6. That's the specific gravity. And in case you ever need this for an exam, specific gravity is the density of a fluid X divided by the density of water. Or if you multiply numerator and denominator by 1 in the form of the acceleration due to gravity divided by the acceleration due to gravity, that's gamma X, specific weight of fluid X divided by specific weight of fluid W. So the specific gravity is given as 0.6. Because it's the ratio of densities or specific weights, specific gravity is dimensionless. So here's our little cube. And again, it's 10 centimeters on a side. And for this cube, first you see that the specific gravity is less than 1. It's lighter than water. You would expect it to float. If the specific gravity were greater than 1, it might sink. So you know that steel has a specific gravity greater than 1. Yet ships float. Why? Because they displace more volume of water than they weigh. So again, if a ship was collapsed into one ball or cube, it would definitely sink. But because we form it into a shape that displaces much more water volume and therefore weight than the weight of the ship floats. So we are basically asking, what is the draft of this system? And we know that, again, this cube has a weight. And the weight would be the specific weight of the plastic in this case times the volume of the cube. It's a uniform specific weight or uniform density material. And that's going to be offset by the buoyant force, which represents the pressure distribution on the bottom. The buoyant force is equal to the specific weight of the fluid, in this case water, times the volume displaced. The volume displaced is not the entire volume of the cube, it's just the volume of the cube below the water line. So again, if you hadn't figured it out, you know, this is the water line. And depth of submergence, H, or draft, as it's also known. So when we whenever you're asked to do a force, whether it's in this course or other courses, the first thing that comes to mind as an engineer should be that you should be doing a free body diagram. And what that does is isolate just the system of interest to you. In this case, our system of interest is the cube. And with that free body, now we want to identify all of the forces that act on it. So the box is our cube in 2 dimensions. You're looking at one end. And the forces acting are the weight and the buoyant force. There are no other forces acting. In the horizontal direction, yes, we have a pressure distribution on each side, but as I discussed last time, that is no different than looking at the forces on a plane submerged surface and looking at the shadow. So the force on one end is going to be this equated by the force in the opposite direction on the other end. So in the vertical direction, which is what's going to give us the depth of submergence or the draft, which is what the question was after, we're going to sum forces, and that tells us that since this object is stable, it's not moving, some of the forces in the vertical direction has to be equal to 0. And those forces, when we look at the sign convention, if the z direction is positive upwards, the buoyant force is positive, and the weight is a negative force because it's acting in the negative z direction. And so when we resolve that vertical static equilibrium equation for this free body, the buoyant force is equal to the weight, Archimedes' principle. The weight, again, is equal to the specific weight of the cube. In this case, gamma c is the specific weight of the cube, and Vc is the volume of the cube. The specific weight of the cube is the specific gravity of the cube times the specific weight of water. That comes right from the definition of specific gravity. And then the volume of the cube is just the length times the width times the height. 10 centimeters times 10 centimeters times 10 centimeters. The buoyant force is equal to the specific weight of the fluid, which we're just calling gamma, and the fluid is water in this problem. And then that's going to be multiplied by the volume displaced. The volume displaced is length times the width, but in this case, it's only the height or the draft that is describing in the vertical dimension the amount of the cube that's below the water in this case. And so in this whole problem, remember, the buoyant force is equal to the weight. So we can equate these 2 lines and actually solve for h. It just drops out of the equation. So basically you have one equation here with one unknown. What's the draft? H. So when we do that and we rearrange, again, this numerator term in the equation below is the weight term. And the denominator term is everything from the buoyant force except h. And if you look at this, we could actually say, remember, gamma c over gamma w is just the specific gravity of the cube, in this case times y. So here you have, that's the specific weight of the cube. That's the specific weight of water. And then 10 centimeters is the total height. As you can see, if we just use the fundamental definition of specific gravity, the specific weight of water would have canceled out and you get the same result. So in this case, 0.6, which is the specific gravity, times the height of the cube, 10 centimeters, is 6 centimeters. So this cube would have 4 centimeters above the water, 6 centimeters below the water. And remember, the weight acts at the center of gravity because this is a uniform density material. Whereas the volume displaced on the left here is the water, and the buoyant force acts through the center of gravity of the displaced volume. Okay. And yes, these do form a couple system, and I won't be going into it this semester because we already lost a week, but this has everything to do with why or why not floating objects are stable or not. So that was the first example. If there's any questions, give me a holler, but I'm going to jump into the next example. So we're going to have a ship, and the ship already has a weight. It's already floating in the water. And what we want to do is add 400 tons to it. And we're asking, what's the increased draft? How much is that ship going to sink in the water if we add 400 tons to it? So the ship is 500 feet in length, and assume it looks like a brick. So it doesn't have nice hydrodynamically pointed bow and stern. So the ship is 500 feet in length and it's 70 feet in width. So the 500 feet is into and out of this slide. And as it's floating now, what you see is there's an area below the water line before you load the 400 tons of 1,800 square feet. I'm giving you that information. And then what we're after is if we add 400 tons, what's going to be the increased draft? How much more is that ship going to sink down into the water? Okay, so we're after H. So the original volume displaced is the 500 feet of length times the 1,800 feet below the water line. And so that's 900,000 cubic feet of water was displaced by the ship before you added the 400 tons. And remember, this is a floating ship. So if we multiply that volume displaced by the specific weight of the water, we now know the original weight of the ship. So again, because this is floating, just like the last example, the weight is equal to the buoyant force, Archimedes' principle. The buoyant force is the specific weight of the fluid, in this case, water, 62.4 pound per cubic feet, times the volume displaced. We just calculated that above to be 900,000 cubic feet. And when I multiply those two together, you will get an answer in pounds. So I just divided by 2,000 pounds per ton to get the answer in tons. So when you do that, what we find is that the original buoyant force and the original weight of the ship is 28,080 tons. And what we're doing is adding 400 tons to it. We could probably add a lot more, but that's what we're adding to it. Okay. When you add the additional 400 tons, you will have a new weight of the 28,080 plus 400 or 28,480 tons. That's going to be the weight after you add the 400 tons. And now we're asking how much further does the ship sink into the water? So again, for the next problem, the force equilibrium in the vertical direction, Archimedes' principle still operates unless H is greater than the side of the ship. So if you put on so much weight that you push the side of the ship below the water line, you've sunken that ship, right? So obviously I didn't give you a limit, but for example, let's say we had 5 feet above the water line. And we're going to calculate H, and what we're going to hope is that at 400 tons, we don't sink the ship more than 5 feet. So what's the new displacement? The new displacement is, again, going to be the original displacement. This is what the ship was displacing before you added the 400 tons. Plus the new displacement. Remember, the ship is 70 feet wide by 500 feet long. We're viewing it as a brick. And the new displacement would be the length times the width times the new draft, H. That's what we're trying to solve here. So that's the new displacement. We have a ship that originally was displacing 900,000 cubic feet. When we add the 400 tons, we're going to displace a new volume. So the sum of those two volumes is the total volume displaced when we add the 400 tons. The new weight we just calculated to be 28,480 tons. That's not only the new weight, but remember, for floating objects, the weight of the object floating is equal to the buoyant force. And the buoyant force is the specific weight of the fluid times the volume displaced. What we have in the line above is the total volume displaced. We have the weight. What we need to do is take this total volume displaced here and here and multiply it by the specific weight of the fluid. This gives us the total weight of the new vessel, and it gives us the volume displaced. So in the previous line, the 28,480 tons is the weight. In the second line, this is the buoyant force. And so the only unknown in that equation where weight is equal to buoyant force is the new draft H. So we solve that equation for H, and what you see is you've increased the draft by 0.37 feet. And as I said before, if we had 5 feet to work with, we only increased it by 0.37. If the ship's just sitting there and the water is nice and calm, you're fine. But if you have 10-foot waves coming at you, you may not be so fine. So again, once we start to look at dynamic situations, things start to change. But this is a very simple example. Okay, so that may be close to the last slide. So again, actually it's not close to the last slide. The buoyant force acts on any object, whether it's partially or totally submerged in fluid. When the fluid is a gas, for example, in air, there's a buoyant force on this pen. But the pressure distribution over the entire surface is just about the same on the top and the bottom. Because remember, the pressure, because the density of the gas is so small, the pressure change from the top to the bottom is not very great. So there is a buoyant force of the gas on this, but for engineering applications, it's negligible. When we start to see the buoyant force more operative is when we're talking about liquids. So, I want to talk a little bit about buoyant weight, and then we'll get to tethering objects, which is more of the engineering application. So you know, when every morning you step onto the bathroom scale, you step on the scale and you see the weight. So for example, if you have a scale rating of 140 pounds, if that's your weight, basically your weight is being opposed by the earth, or the bathroom scale in this case, and you have a force equilibrium, and that's why the scale reads exactly your weight. If you drew a free body diagram of the scale, just the scale, you have the weight of you standing on it and the ground pushing in the other direction, and that's what the scale is reading. No other forces acting. If you then jump into the pool and completely submerge yourself, now you have a buoyant force operating on you because you're submerged in a liquid, in this case, for example, water. And so now when you look at some of the forces in the Z direction, before it was just the ground and the scale, or sorry, your weight and the scale. But now there's a buoyant force operating. And so what it means is that your weight is now located in two different places. The scale will have one reading and the buoyant force is another, and the sum of those two reactions gives you the weight. So for example, if you had a buoyant force of 138 pounds on you, your original weight in air is the 140 pounds. The buoyant force is 138 pounds, which means the scale, if you were standing on the scale at the bottom of the pool, would only read 2 pounds. Okay. In the old days, and when I say old days, we're talking medieval, one way to identify if a crown was gold was to weigh it in air and weigh it in water. And what would come out of this equilibrium pair of equations would be the specific gravity or the specific weight or the density of the metal. And back then they knew what the density of pure gold should be. And so they could tell if it was a fake or not. So for a submerged object, so you take a cube, a brick, a real brick, and you put it in water, you have not changed the mass. What happens is the apparent weight changes because of the buoyant force. So the mass stays the same. And that gets us to tethered objects. So for example, you could have a floating object. And in this case, the weight is equal to the buoyant force. However, you could tether this object. You could pull it under the water and completely submerge it. It wants to float. But in this case, the tether in this case is that line. So for example, you anchor this to the bottom of the ocean, the bottom of a lake. And now, if again, whenever you are talking forces, for this object, we have the weight counteracted by the buoyant force. And that's what comes out of some of the forces in the Z equal to 0. Similarly, for the tethered object, now you have a new free body diagram. There's a new force acting, and that's the tethered force. And we could design what would be the restraining force necessary to keep this underwater, or we could size the cable or the fastener system that would need to create this system steady state. So in this case, when we look at the force equilibrium in the vertical direction for the free body diagram, it tells us that the buoyant force, which always acts in the positive Z upwards, minus the weight, negative Z direction, minus the tether force, negative Z direction. It's pulling down on this object to make it go under the fluid, had to be equal to 0. And so 3 ways to look at this. One is to solve that equation for the buoyant force. One is to solve that equation for the weight. And on the next slide, you'll see we can also solve it for the tether. It depends on what you're being asked. But they all start the same place, that free body diagram. So again, we can certainly maintain what would normally be a floating object submerged, but we're going to have a tether force to do that. So again, here's an example of a tethered system. And again, this object wants to float because the buoyant force on the submerged object exceeds the weight. If you didn't have the tether there holding it in place, the thing would pop up to the surface. So again, we do a force equilibrium on the free body diagram, in this case, the sunken buoy. And we can either solve that for the buoyant force. This is what was on the previous slide. We can solve that for the weight, or we can solve that equation for the tether force. And again, it depends on what the problem is asking. In an engineering design, you probably might be after the tether force and then trying to figure out what size cable you need in order to hold this thing under the water. So the opposite of a floating object that you are pulling under and keeping it submerged would be an object that normally would have sunk. So think of a rock. You throw that into a pond and it sinks right to the bottom. Why? Because the weight exceeds the buoyant force. So in this case, that's why the rock sinks to the bottom. And what you would have if you didn't do anything on this free body diagram, so here's a free body diagram of this rock. It has a weight. There is a buoyant force acting on it, but there's also a reaction force. And that would be the reaction force of this thing sitting. Basically, this would be the submerged weight, is what it is. This would be the weight of that thing sitting on the bottom. And in this case, the weight of this object would be equal to the sum of the reaction force and the buoyant force. Now what we would like to do is take that object and pull it off the bottom and just suspend it somewhere in the water column. It could even be partially suspended. And to do that, we obviously need something that's going to pull it up from the bottom and hold it there. And again, we'll call that a tether. It's something that's holding it. And now the free body diagram has, as before, the weight, as before, the buoyant force. However, now that reaction force is gone. It's not sitting on the bottom. And what replaces it is the fact that you have this tether force acting upwards in the positive z direction. So when we look at the sum of the forces in the z direction here, some of the forces in the z are 0 because this thing is just being held suspended above the bottom. It's equal to the tether force, positive z, buoyant force, positive z, minus the weight, negative z. And again, you can solve for either one of those three, the tension force, the buoyant force, and the weight. It's not uncommon to use a buoy to maybe support something like that. And again, it's sunken because the weight normally would exceed the buoyant force. It would be sitting on the bottom. When we tether it, we would have a free body diagram indicating the force balance. And again, this is a free body diagram of just this object. And so we can solve for the weight. And we would see that the weight now has compartments, which is supporting it. One is the buoyant force, and the other is the tension in the cable. Now, I want to identify that I haven't talked about that. So I basically assume that the weight and the buoyant force on the buoy, that's this guy up top, is negligible. But if you actually looked at the free body diagram of this, what it does is affect the tension. Okay, so you can actually be supporting some of the tension instead of in the cable, but by the buoy itself. Okay, so I didn't look at that. I just want to bring that to your attention. You can start to make these problems more complicated. And you just have to understand, you know, each component that you're analyzing. In that case, they're interconnected. So I want to talk about an example using this knowledge. So you're on a ship, construction ship, building a module below the ocean on the ocean floor. And it's being built out of concrete panels. So you lift the panel off the deck of the ship and you swing the crane arm over the side of the ship, and the cable lowers this panel into the water and down to the bottom of the ocean where people can fabricate this building. Okay, so the panel, a concrete panel, and I give you the specific weight of concrete, 150 pounds per cubic foot, pretty common. The panel has dimensions 10 feet in height by 20 feet in length, and it's 2 foot thick. And this is what the system looks like. So again, you can see the ship, and you can see how it's being tethered in this case. And you've got this panel, which is going to have a weight, and there's going to be a buoyant force on the panel. So again, we could just isolate that 10 foot by 20 foot by 2 foot panel. That's our free body. And then start to identify all the forces acting on it. And the question in this case is, what's the tension in the cable at this particular moment? What's the tension in the cable when it's just sitting like this? So there's our free body diagram of the panel. So again, this is 10 foot by 20 foot, and it's 2 feet into the paper. And the free body diagram, again, indicates the three forces, the tension force, the buoyant force, and the weight that we've been discussing for the last 20 minutes. The weight of any object is always equal to its specific weight, gamma. So this is the specific weight of the concrete. And then this is the volume of the concrete, 10 foot by 20 foot by 2 foot. Obviously, this assumes that the panel is all concrete. It's a uniform specific weight structure. You could certainly have something that's not a uniform specific weight structure. Somehow you're going to have to calculate its weight. So for example, it could have been a steel sphere, which is hollow. That's not a uniform specific weight material. So that's the weight. Buoyant force. Buoyant force is the specific weight of the fluid in this case, which is water. And if you ever see it, seawater doesn't have the same specific weight as water, right? Seawater is a little heavier. So this would be the specific weight of the fluid in this case, and all of this is the volume displaced. And because it's completely sunken, it's the same volume as the volume of the panel. It's all underwater. So you can see in this case that the weight of 60,000 pounds is greater than the weight of 24,960, almost 25,000 pounds. And that's why this concrete panel would just sink and it would go right to the bottom. And the difference between those two is the weight that the bottom would be supporting for this panel. However, we don't want it to go to the bottom. What is going to offset these two is the tension force. So in this case, again, from the free body diagram, sum of the forces in the vertical direction is 0, would be equal to the tension plus the buoyant force minus the weight. We just calculated the buoyant force and the weight. So we can isolate the tension to calculate what the tension is. So the tension is the weight minus the buoyant force. And that would be our 60,000 pounds minus our almost 25,000 pounds, which gives us 35,040 pounds. And again, I just did this again algebraically. The weight is the specific weight of the concrete times the volume of the concrete. And because it's submerged, the buoyant force is the specific weight of the fluid times that same volume because it's fully submerged. So that would be the tension in the cable. So pause because I'm waiting for questions. What happens? So before this thing was just sitting there. What happens when we're raising the panel? Are we going to see the same force, more or less? We're going to get to this near the end of the semester. But once this panel starts moving, everything up until now was static, was not moving. Once this panel starts moving, you now have a drag force on it. The frictional resistance between the physical surface of the concrete and the fluid. And that drag force opposes motion. So for example, if we're pulling it up through the water column, the drag force is in the opposite direction. You can still do a free body diagram as long as you have steady state. So if this is coming up at a constant velocity, that's a steady state system. And when we have a steady state system, some of the forces in the z direction, positive upwards, still is equal to 0. It's just that we have this drag force now acting on it. So if we do a free body diagram, here's the panel. And it had a weight. It had the tether force before, and it had the buoyant force. But now because you're pulling it up, it's got a drag force. And again, the drag force is the frictional resistance between the exterior skin of the concrete panel and the fluid. So in this case, when you perform sum of forces equals 0 and solve for T, if you were pulling this up, what the drag force does is to increase the tether force. If you were lowering it, you would expect the opposite. If you're lowering, then the drag force again opposes motion. And we're going to spend 2 or 3 weeks on drag in here. Drag force is in the opposite direction, and that means that it would be much less tether force when you're lowering. What would be the largest tether force you would have? Well, the largest tether force would be when this isn't submerged, when it's sitting on the deck of the ship. When it's sitting on the deck of the ship, it's weighing 60,000 pounds. You're going to pick it up. But the only thing operating when it's out of the water is the tension in the cable and the weight. Because it's not submerged in the water, when it's sitting on the deck of the ship, there's no buoyant force. And the drag in air, even if you're moving it, because air has very, very low viscosity, we can probably ignore that drag at these velocities. So when it's out of the water on the side of the ship, that's actually your biggest risk of failure, right? Unless you decided you had to drag this up at an incredibly high velocity. You could certainly create a drag force so large that it would make a tension in the cable larger than that 60,000 pounds of weight. Okay, and so, they have entire professions that deal with tethering and figuring out how you lift, buckle things together and drop things. And it's all revolves around understanding how forces are changing when you're actually moving things around. It's not a trivial issue. And right now we're just talking force equilibrium. How many times have you seen in the news a crane that has collapsed? Typically, that's a moment equilibrium. And what people neglect to think about at that time is the force equilibrium may be okay, but the moment equilibrium may not. And all you need to know, these same forces are acting, but you need to know about the point of rotation in which they act when you're trying to do a moment equilibrium. That would be the difference. So I think I finished that. I'm going to keep that, and I'm going to open up in the last 10 minutes, I want to start a new topic. And remember, I mentioned this last class, and I'll mention it again. Wednesday's lecture, 2 days ago, today's lecture, not on the exam, or the next exam. This is a competition, so I think it's in Philadelphia. They, for charity, will have different bartenders try to slide a glass of beer and see who gets closest to the end of the bar without spilling anything or knocking the glass over. But what I want you to focus on is this. Here's the quiz for today. Competition between the 300 people in the class and everybody online. What do you notice about the surface of the beer? Is it horizontal? Okay, so the people in the class are all shaking their head no. Okay. What's happening here that is different? Because before, what we identified is that when we had a fluid, we were always drawing a horizontal surface. What's different about this? And what's different is we are employing an acceleration field. And this is the handout for today. We're employing an acceleration field to a finite fluid volume. And when we do that, the laws of fluid statics need to be modified. Why? Because before, under this scenario, the only acceleration was the gravitational field. And under this situation, you have not only gravity, but you have the AX, an acceleration in the horizontal direction in gravity. So you have this new acceleration field. And that is going to dictate pressures. So basically, what I want to discuss, and I know I won't get through this today, bring or have your handout available next on Monday. Basically, what we're trying to describe is the laws of fluid statics can be modified to apply to moving bodies of fluids, subjected to acceleration fields in this case, with the only caveat is that there's no relative movement between the fluids in the finite fluid body or between the fluids and the boundaries. In the case of the first slide, the glass, there's no relative fluid movement. And we'll talk about relative fluid movement a little bit later. So we're just turning that off for now. So we start at the exact same place, and this is all on your handout, that we did with fluid statics. We are going to start with a differential sized cube. And the cube is dx by dy by dz. But instead of looking at a three-dimensional derivation, we're going to look at a two-dimensional derivation, just like we did before, and say that whatever happens in the x happens in the y, since they're both horizontal coordinate axes, And because Z is collinear with gravity, that is distinguished separate from X and Y. So we have this acceleration field. So for example, consider this differential cube a little differential cube of what's in the beer glass. We're going to have that cube subjected to some acceleration field. And what happens, just like in fluid statics before, we're going to assume that pressure varies as we move through space. It can vary through the horizontal dimension, or it can vary through the vertical dimension. So what did we do before? What we did before was we looked at sum of forces in the horizontal and the vertical directions being zero. Why? Because we had a system that was static. It was not moving. In this case, what we recognize is that this differential cube is being accelerated. So instead of sum of forces equals zero, in this case, in every direction, we have to say that the sum of the forces is mass times acceleration, Newton's second law. And we will perform that in both X and Z directions. So I said I would leave some time for any questions you may have due to the anxiety buildup. I'm going to stop there and continue with this next time. And are there any questions from in the class or online about anything? They're either slow typers or no questions.
We have one person wrote conservation of momentum, but I don't know if that's a question.
Sum of the forces equal ma is conservation of momentum. Yep.
Someone says what time is the exam? It's at 2 o'clock.
Exam is at 2 o'clock, and I believe everybody was assigned to one of 3 rooms.
And they want to know how many problems will be on the exam.
The number of problems on the exam will be between 5 and 10. Very similar to homework problems. No theoretical derivations.
And then will we get an equation sheet?
You don't need an equation sheet. Every equation you need is in your book, and it's an open book exam. 1 crib sheet. Any tables you need are in your book. If you do not have the latest version of the book, there are older versions of the book. If you have a different fluids book, I'm pretty sure that the information you need would be in that fluids textbook. And at the end of the day, if you have any question, if you don't understand a problem, the best answer, if you ask one of the TAs, the answer you're going to get is make an assumption about what you think the problem requires. So if you think it needs a specific weight and you can't find that, make an assumption about it and get on with your life. Remember, 80% of the problem points you will get is setting up the problem, not crunching numbers.
And then we got, is buoyancy on the exam? We started to talk about it a week ago.
Today's lecture and Wednesday's lecture are not on the exam.
How's that right now?
I will leave this open for a minute or two while I shut things down, but unless I hear more questions, that's it. Good luck this afternoon. Music to my ears. Good. So, stop share and then end.